Welcome back to the next video on the properties of solutions. Continuing where we left off, we're going to go ahead and add a bit of a complication to the situation we saw with diffusion. Let's say that we have a solution and we put a barrier up inside that solution. And it's going to be a very specialized kind of a barrier. What it will do is that it will allow certain substances to cross from one side to the other, but it will prevent other substances from crossing entirely. We call such a barrier a semi-permeable membrane. Semi-permeable membranes are very important in biological processes, and perhaps the most important of all of these is going to be the cell membrane, and some of the membranes which exist within cells themselves, the intracellular membranes, which have to be very restrictive in what they allow to go into a cell or what is allowed to leave a cell. Now let's say that we have two aqueous solutions with a semi-permeable membrane in between them. And the only thing that semi-permeable membrane is going to allow to go from one side to the other is the solvent. So if it's an aqueous solution, the solvent will be water. So water molecules are allowed to go from one side of the barrier to the other. Nothing else is allowed to. And so that's the most common type of the membrane we're going to study. Now let's say that we have an imbalance between those solutions. Let's say that one side of the membrane has a higher concentration of solutes than the other. For example, let's say that one side of the membrane has 1 molar sodium chloride solution in it, and the other side of the barrier, instead of having 1 molar sodium chloride, has 2 molar sodium chloride solution. So there's a difference in the concentration between the two solutions. What will happen is that water will flow from the side with the lower concentration of solutes to the side with the higher concentration. So we call this process osmosis. Osmosis. So water is going from the side of lower concentration of solutes to the higher concentration. Another way of looking at it that I think is a little more confusing is to say that water is actually flowing from the side of higher concentration of water to lower concentration of water. But that makes it, as I said, needlessly complicated. So what we're going to find here is that water will always follow the solute. It will go after the side with the higher concentration of solute. So now let's think about this. We said we had a 1 molar concentration on one side and a 2 molar concentration on the other. The water will flow from the side with lower concentration to higher concentration. So as water leaves the side with lower concentration, what's going to happen to the concentration of that side? Well, as water is flowing away, the volume is becoming smaller, but the amount of solutes is not changing. That's essentially the same as saying, when we look at molarity, that the numerator stays the same, but the denominator gets smaller. So what happens in that kind of a case? Well, the concentration gets larger. What happens to the other side? Water is flowing to the side with the higher concentration. Its volume is doing the opposite. Its volume is increasing while the amount of solute stays the same, because again, solute can't cross the barrier. So you're making the denominator larger, so you are lowering the concentration on that side. So the side that had the higher concentration is now, its concentration is getting lower. The side with the lower concentration, its concentration is now getting higher. And this process would continue, if possible, until they essentially have the same concentration. Or what we find is, since one side, the liquid is going from one side to the other, that's actually causing a weight imbalance between the two solutions. So gravity might offset that, and there might come a point where the process has to stop. This is related to the concept of osmotic pressure. And osmotic pressure essentially would be the amount of pressure you would need to apply to force the solvent back to the side with the lower concentration. So let's do another visual demonstration. And I really liked those Amoeba Sisters videos so much that I'm going to go ahead and give you another one to take a look at. So I'm going to give you a link here in the window or below, and it is on the video describing osmosis and water potential. Now, you don't need to worry about the calculations on water potential. They don't figure into anything that we are going to be doing here. You also don't need to worry too much at this point about active and passive transport. That's something that you should definitely be learning about in physiology, but it really wouldn't hurt to watch it. So it's another great video. I hope you enjoy it.